our discussion on ideal gas thermometer, where we have seen that thermometer. So we have seen that um, limit. Okay, let's continue our discussion on ideal gas thermometer. We have seen that limit P tends to 0 is equal to a constant which depends on temperature. So we can plot this. So we have here C of T, and this is temperature, and we know that this value, that is to temperature T. So basically this will be the slope, and it's a linear interpolation as we have seen. So it is 0 Kelvin here, and at this temperature, this is C of TTP. So the temperature corresponding to a triple point of water. So that will be 273.16. Now you can write the equation for this curve, C of y minus, like for example, we have here x1 y1 and x2 y2. So basically y of t is equal to slope. Slope will be uh, this y is C of t of tp minus 0 by t minus 0, so that we get the same as I wrote into temperature. So this will give us temperature. So here C of t is equal to RT, and this is a limit. So here we are considering molar volume, basically volume of 1 mole of gas. So when we are using this property for real gases, the pressure has to be very small. It has to be tending to 0. Otherwise, the real gases will deviate from this expression, that is RT. So this will be deviated, and this is the property of ideal gas. So for ideal gas, even if pressure is not 0, then also this condition will hold true for ideal gases. And here we can see the state functions that are related are pressure, volume, and temperature. So even if pressure is not equal to 0, it is applicable for ideal gas. But in the case of real gases, it doesn't hold true. Let's see why. So for real gases, there are different constraints that exist for real gases. So for real gases, the real gases, the gas atoms or molecules repel in each other if they are compact, and if the gas is not so compact, then so for real gases, the atoms and molecules of the gas interact with each other, and there could be either expansion or compression. So there are three different equations developed to address those constraints. Firstly, by introducing a compressibility factor to this. So basically, it's a real gas of 1 mole, volume of real gas, 1 mole of real gas is equal to Z or T. So here we have Z. This is a compressibility factor. Now, if Z less than 1, this means that the volume would be less due to the gas is compact and there is attraction between the atoms and molecules. So here gas is more compact due to attraction, and if Z is greater than 1, the gas molecules or atoms are repelling each other, hence they tend to have a bigger volume in this case. So this equation gives tells about that attraction and repulsion in this way. And the second equation is virial expansion. Basically, all three equations independently try to correct that equation of ideal gas. So here PV real by RT. So that factor, whichever is there, that is the virial expansion factor Z. This will be is equal to so here first virial coefficient and this is the second virial coefficient, and these coefficients depends on the temperature. Now we can also draw a function for b of t, for example, in this manner. So we have b of t and here temperature. So at this point b of t is equal to 0. So here it behaves like a ideal gas at this particular temperature. and above this temperature b of t is positive, and below that it is negative. And these higher order terms we can neglect because they have a negligible effect on this equation. Now the third equation is the van der Waals equation, and it's more closer to the actual behavior of real gas. So this is the third equation, and this is more important because it relies on two parameters unlike the previous ones. So what are the two parameters? The first parameter, like before, it is the attraction and repulsion. That is one factor. Also, it will consider the volume of gas, individual gas atoms and molecules. So if there are more number of atoms or molecules in a gas molecules in a container, they occupy the volume, and they will contribute for reducing the volume for other atoms or molecules. So in that case, the equation is 1 mole is equal to RT. So now we have to now the actual volume that is available is reduced, and that is represented by B here. So because each suppose if it is a container and there are molecules, so these will also occupy the volume, and they will contribute to reduction to a factor of minus B. So this is that. And secondly, the other factor is attraction and repulsion as addressed in the previous cases. So because of attraction or repulsion, the pressure would be reduced, and that will be is equal to RT by uh, this much minus A by. So this is the pressure. Now when we rearrange, we get multiplied with this one, we get RT. So now here the value of A depends on the attraction or repulsion. So if A is greater than 0, there is attraction and the pressure will be increased. And if A is less than 0, there will be repulsion and the pressure would be reduced because of that. So this is all about the ideal gas thermometer and the correction when we use the real gases. Calculate this problem regarding ideal gas thermometer. It can also be called a constant volume thermometer or Boyle's thermometer because it is based on ideal gas law, and ideal gas law is nothing but Boyle's law. So in the first problem, we have given that ideal gas thermometer used to measure temperature at triple point of water temperature. The gas pressure is 1 atmosphere. When the thermometer is placed in unknown environment, the pressure drops to zero point 0.7 atm. Then what is the temperature of the environment? So we know that PV is equal to RT, and as it is a constant volume, um, thermometer V is constant, and we know that R is gas constant, so this is also constant. So P is directly proportional to temperature. Now in this case, P1 by P2 is equal to T1 by T2. So P2 is equal to P1 into T2 by T1. That gives us P1 is 1 atmosphere pressure. T2 is uh, sorry, here we are supposed to find the unknown temperature. So T2 is equal to T1 into P2 by P1. So that will give T1 is triple point of water, P2 is zero point 0.7 by 1. So that will give us the second temperature for this problem. Now let's look at the another problem. A gas thermometer has an initial pressure of 2 atmosphere at 300 Kelvin. The temperature is increased to 500 Kelvin. So find the pressure. Same as we did before. Final pressure of P, suppose P2 by P1 is equal to T2 by T1. So that will give us P1 is 2 and T2 is 500 by 300. This will give us 3 point, basically 3.33 atmospheric. Now we have another problem. An ideal gas thermometer reads a pressure of zero point 0.5 atmosphere at 100 Kelvin. What will be the pressure be at the triple point of water? So here the question is like, what would be the ideal gas thermometer pressure at triple point of water temperature? So at that point, what will be the pressure of this ideal gas? Basically, so here the question is like, what is the pressure of the ideal gas? So it will be P2, T2 by P1 is zero point 0.5. It is 273.15 by 100. So we get that respective pressure. Um, Now here at absolute 0 Kelvin, the pressure of an ideal gas is 0. Now if an ideal gas thermometer shows pressure of zero point 0.5 atmosphere at 200 Kelvin and zero point 0.7 atmosphere at unknown temperature, what is the unknown temperature? So this is same as earlier cases how we solved. Now this one is quite interesting. So here we have given the ideal gas pressure at 300 Kelvin, which is 1 atmosphere, and also we have given the volume of 1 mole of gas. Now we have to verify the ideal gas law and calculate the gas constant from this. So we know that ideal gas law is PV nRT. So when there is n number of moles, but when we use 1 mole, this is a volume of 1 mole of gas is equal to RT. Now here R is equal to by T. Now we have given V is given as 22.41 liter per mole. So the volume is given in liters. We have to convert into meter cube. 1 liter is equal to 10 power minus 3 meter cube. So here R would be, we have given the pressure as 1 atmosphere, and molar volume is 10 power minus 3 into 22.41, as it is 22.41 liters by temperature 300 Kelvin. Now when we do this, we will get value of R. Do calculate and write that in the comments what is the value of R based on these calculations. Also, work on the units of R and convert into standard units, that is joule per mole Kelvin. So how we can also think of the units here. How would be the units for R? So for is so we have pressure in SI units. Pressure is equal to force per area. So or else P multiplied by P. So what is let's figure on the units of this. This is meter cube per mole. SI units of molar volume is meter cube per mole, and temperature T is Kelvin. But we have the pressure here. We are using the pressure as atmosphere, but we have to convert that into SI units. So we know that atmosphere, one atmosphere in Newton per meter square. So that is important for us here. Mm, Basically, one atmosphere is equal to 101,325 Pascal, or uh, actually 1 Newton per meter square is called as 1 Pascal. So this is the SI unit of pressure. So here we have 1 atmosphere, which is equal to 101,325 pascals. We have to substitute that in the SI units into 10 power minus 3 into 22.41 by 300. So when we do multiply this, let me calculate from my end. So it is like 7.568. 7.568, we have pressure, sorry, pressure times more volume is joules, but we have, it is meter cube per mole. Basically P times this units is nothing but joule per mole, because PV is joules. So it is joule, and at denominator we have temperature, so Kelvin mole. So this is how we got. So this is somewhat closer value of gas constant, and nevertheless do not bother about the value, but please see the conversions of SI units and how we can represent the units of R and why it is joule per Kelvin per mole. And we have arrived at this closest answer because we have converted into pascals, and then substituted them, and also we have seen the units accordingly. So that's the units of gas constant basically in SI units. Even if it is given in another units also, you should be able to convert by based on this understanding. Thank you so much for watching this video. In the next video we will see more concepts of thermodynamics.